Hi everyone, welcome back to homework 4 part 1. So we just did the NRTL activity coefficient model with Python loops, and now we're going to look at it with this thing called Einsum. And we're going to use this numpy.einsum, um, which I guess just reading here, it allows us to represent multi-dimensional linear algebraic array operations in a simple fashion. Um, and we're gonna need subscripts. We're gonna need operands, and it looks like it will evaluate the this thing called the Einstein summation convention on the operands. Um, and it's a little bit confusing what it does, but I think it'll make more sense when we get into it. So I'm just gonna hop in. Now, one thing I want to address real quick is that in the last video, we got these numbers for our activity coefficients. And actually, I made a small mistake. This term 2 here, we basically need to add our new value to the old term 2 because we're doing a summation. And I forgot about the summation. And if we look up here, it's the summation right here that I forgot about, this big one. So I'm just going to say plus equals here. And these should change, not by a whole lot, but we get 0.99, 1.14, and then 1.6. So just that small mistake, just fixing that real quick. And now what I want to do is I want to start with the Einsum method. So we're going to go ahead and define Einsum. This function is going to take in this x and this t. Just like before. And now we're still going to need tau, we're going to need g, so I'm just going to copy and paste those, since we already coded those. Again, these are just from up here, g, tau, and we're just going to be doing this again, but with the Einsum method. Okay, so for the first thing, we want to start with this up here, this x tau g. So we'll call this x tau g. We're going to be doing this kind of the same, kind of in the same way we did this one with loops, where we start with x tau g. And we're going to use this Einsum, so np.einsum. Now the way the Einsum, this Einsum thing works is, so it's going to take in, basically we have this x that has the j subscript, and we have this tau g which have the ji subscript. So we're going to come down here, we're going to put in j, and then we're going to put in ji, and we want it to put the arrow. Once this is all done, this gamma, it only has the I subscript, so we're going to come down here and put I. So that's telling us, it's basically telling the function how to treat the subscripts. And then we're going to put x, because x has the j subscript. And then we have a tau times g, which has the ji subscript. So that's going to be our x tau g. We're going to do the same type of thing for xg. np.einsum. Scroll up here. Ki. This is the same thing as j and ji. So we have j, but we need quotes, j, ji, arrow to I. We have x, and we have g. So far pretty straightforward. And then we just have this term 1, just like before, equals x tau g divided by xg. Okay, so that's going to be our term 1. Now we need to come down here and do term 2. The thing about term 2, it's going to be a little bit different. Just like the loop method, this right here, this expression, is equal to term 1. It's the same thing. So we're going to have this tau ij minus term 1. Now, it gets a little bit tricky because this tau and this term 1 are going to be different sizes, different sized arrays. So if we want this done correctly, we're gonna kind of have to, I guess, specify specify how we want the subtraction done. So I'll call this term 1. And that's why we will come in here and we'll put none. We're basically just telling Python where in the array we want to actually do this multiplication. So instead of throwing us an error, it will actually do the multiplication we expect. We want to divide by xg, just like we did here. This is xg right here. So we're taking this tau minus term 1, dividing it by xg, because xg is this. We already did the math on that. And then we're going to multiply it by g. It's g on the top here. So we'll say g times. And this is going to be our expression for this. And the reason why I don't include x is actually because of the Einsum function. The Einsum function requires basically 2 inputs. So like here we have x and tau times g, x and g. What we're going to do for this term 2, we're going to have x, and then we're going to have the whole rest of the thing. So x is in terms of, or it has the j subscript. Everything else is going to be ij, because we have ij, kj, but it's basically the same thing as ij. We have ij, and then we have this term 1 here, which is basically ij as well. So I'll come back down here. So what I'm going to want to do here is set up this term 2 equals np.einsum, and we're going to have j and ij goes to I. So j and ij goes to I, and then we're going to have x. I need a quote there. So we're going to have x, and then we're going to have the whole rest of the thing. So that will be our term 2. And then basically all we have left to do is to return term 1 plus term 2. And then if we'll call this Einsum. We'll just call it Einsum, it doesn't matter. Einsum with x and with our t, which is 300. And it returns the natural log of the activity coefficients. So we will np.exp. And if we look, 0.99, 0.99, 1.14, 1.14, 1.6, 1.6. So actually doing the Einsum method, we get the exact same answer as doing this Python loop method. But I mean, this is a lot simpler. So yeah, that's the Einsum method. And then all we have left is matrix vector multiplications. Okay, so for matrix vector multiplications, I'm going to go ahead and define a new function. We'll just call it the MV method. matrix vector method. And we're going to still have that x and that t again. Mole fractions and temperature. I'm going to copy and paste this tau and this g again. And then we're just going to start with x tau g again, just like we did in the Einsum. X tau g. And x tau g is going to be equal to x and tau. So x has the j, and then tau times g has the ji. So this is going to be equal to x matrix multiplication with tau times g. Okay. X and tau times g. And then we're going to have xg equals x with the k matrix multiplication with g with the ki. Xg equals x, leave the space in there, g. And then we're just going to have term 1 equals x tau g divided by xg. So, I mean, it's pretty simple so far. Just doing matrix multiplication. Okay, no errors, that's a good sign. And now for this term 2 here, again, this is just tau minus term 1. So we're going to come back and do tau minus term 1. So tau minus term 1. Just like before, we're going to have this none to specify where, like, how to do a multiplication. Parentheses. And then we're going to divide by xg. None. Just like that. And I'm going to multiply by g. So far this is looking pretty similar to the Einsum method. We're setting it up in the same way. And then I'm just going to call this, we'll just give it some placeholder name. We'll just call it n, I guess. So right now we have this x here, and then the whole rest of the term here is equal to n. So we're going to do x cross n, or x matrix multiplication with n. So now we have term 2 equals n matrix multiplication with x. And then I believe this should... Right now these are different sized matrices. If I type n here, I don't... what if we just do that? N. I just want to look at what n is. I don't know. N is going to be a 3 by 3 matrix. Just based on this here, this tau is a 3 by 3 matrix. And when we do all this, we end up with still a 3 by 3 matrix. So right now n, or x, is this. So we're going to need to use the transpose of x instead of x. So we'll say term 2 equals n matrix multiplication with x dot t. And actually what I'm going to use is this squeeze to kind of get Python to do it correctly. So the squeeze there, And then we're just going to return term 1 plus term 2. And again, we're just going to use a squeeze on this to get it in the right dimensions. I think it's np.squeeze actually. MV method x 300. So we get a 3x3 array, which I think this should not be. Oh, I think one thing I forgot to do, we need to reshape x into an array with the dimensions 1 to -1, just to get Python to kind of treat the array correctly. Oh, I'm still getting... I'm curious if I just go ahead and do the exponent here. We're still getting an error here. Just go through everything real quick. xt reshape 1 x tau g equals x cross the tau g. Times g. Just in case there's some weird thing going on there. Oh, okay. Yeah. Okay, so then we get the natural logs of the activity coefficients, and when we do the exponent, when we do e to those values, we get 0.99, 1.14, and 1.6, which is the same thing as up here, 0.99, 1.14, and 1.6. And actually, it looks like it's the same for quite a few decimal places as far as Python's showing right now. So here we have the Python loops method, the Einsum method, and the matrix vector multiplication method. We did all 3 of them, 1, 2, 3, and we actually ended up with getting the same answers all 3 times. So that was part 1, and I will see you in part 2.